Yep, hello. All good? Okay, I'll use that as my trigger to get started anyway. So those of you that are just making your way in, if you could do so quietly, that would be really appreciated because we're just running a little bit behind time already. Yep. So to get started for this session, we've got Aleksi, who's going to speak to us about ordinal regression for hierarchical survey data. So I'm going to hand over to you, take it away, and look forward to it.
Thank you. Hello, everyone. My name is Aleksi. I'm a first-year PhD student from University of Turku, and today I will talk about probabilistic ordinal regression for hierarchical survey data. So, first of all, a small introduction. What's ordinal data? If you do not know, most of you probably do, but it's like this categorical data where there's some natural ordering to the categories. So, if you have ever filled in a survey, there's this like a scale questions, like you have to rate something from very good or very bad, for example. And this is something that then has to be taken into account in the modeling, and these types of obviously variables are common in surveys, and then there are some problems that can arise when analyzing this type of data, especially when the sample sizes are small, and which can then lead to like these stable category probability estimates for some of the categories. And when doing hierarchical modeling, if there's only few clusters, or maybe only few cities or countries from which this data has been collected. So I will talk about how probabilistic modeling can help answer these problems. We obviously know all know the benefits of probabilistic modeling already, so I don't have to talk about general benefits too much. So the data sets I've used in this, I will use are these two survey data sets collected as part of this OpenMuse project. This is this live music census collected in 5 European countries, and then this cultural access and participation survey collected in 5 different countries. So these are both hierarchical in structure because they were collected in different cities or countries, and then they also contain several ordinal scale items that can be then demonstrate the benefits. So here I have a few examples that may be one of the problems that I faced when analyzing this data. So first one is from the live music census. It's this answer to this question of how was your night by city, and we see that there's, well, obviously some of the cities have quite few answers, and then we see that some people, not everyone had quite good night. No one answered that they had very bad or bad night, but then that can cause problems in the analysis. And then also from the other survey, we have this question of how would you rate the live music scene in the city. And here we see that obviously there is some variation how people answered different countries. So we see that people in Italy answered average more than the other ones. So we should then take this into account when analyzing this data. So the model I've used to analyze this data is this quite simple, quite nothing too fancy. This hierarchical cumulative logistic model, it's very common approach for analyzing ordinal data, and it's in PRMS, so it's commonly available. And it works by modeling this latent variable, which is then partitioned by these threshold variables alpha, that then tell which answer category that response belongs or is modeled into. And then there is this, so there is no common intercept term like in, sorry, like in normal regression modeling, instead we have these threshold parameters, alpha j, and then we have the random cluster, random intercept term for the different clusters. So because there's these different threshold parameters, we could set common prior for all of them, but I think it's better to set a separate one for every of them, so because that gives us more control over the prior distribution. So if there's 5 answer categories, then that means there are 4 of these threshold parameters, and I've set them in a way that the category properties are roughly equal priori without. And then for the clusters, I've used this half normal distribution because there's only 5 clusters. It helps to regularize the modeling because otherwise it can start to run problems if it's more loose. So here I have some prior predictive checks with 4 categories and 5 categories. So we see that in both cases, the middle categories get a little bit more prior, like the assumption is they have a little bit more answers than the answer categories in their edges. So I think this is quite reasonable assumption. Obviously, we could tune this more to be like they actually are equal, but I think this is okay. So then I did some simulation to test how this performs this with the different clusters, so structures. So I did 50 replicants of each, and with 300 sample size, I did this one where all the clusters had equal amount of answers, and then I did one where one of the clusters had only few answers compared to others, and I did this one where there was a lot of clusters, all equal amount of answers, and then I did where some of the clusters then had less answers. So to see how the models perform when there's a lot of clusters and few clusters, and when the clusters are equal and when the clusters are unbalanced. So if then we look at the estimates for the standard deviation between cluster and standard deviation, we see that the Bayesian model slightly gives, when there are only few clusters, it gives slightly over like too large estimates, and the classical one gives quite low estimates. That underestimates the deviation by quite a lot. And when there's many clusters, the Bayesian does quite well in estimating the standard deviation in comparison to the classical one that still undervalues the true deviation. And then if we look at the estimated standard deviations from the surveys, we see that the Bayesian model gives quite a lot of, or gives larger estimates for all of these questions that I have modeled here. And if you then look at the previous slides results where the Bayesian model gave slightly overconfident results, but or too large results, and the classical one gave too small, I think we can then also maybe assume that it's this case with the real data too, that the classical model underestimates the standard deviation, and then Bayesian model is closer to the truth and is better able to capture the between cluster deviation. And then another problem that is with the classical approach is that the models can run into convergence problems, that the estimates don't converge at all when there are few clusters, and especially if we drop the sample size down to 100 from 300, then even 4 of those in the simulations, the classical model was not able to provide a reasonable estimate for the standard deviation, and obviously then the Bayesian model did not have similar problems. And then as I was showing earlier about the fact that some of these for some of these questions, people did not answer every category, like here, this how was your night, that people did not answer very bad or bad. If we use the classical approach, then the model is not able to provide estimates for these 2 missing categories, so it just drops them from the model and results. But if we use the Bayesian approach, because we have the prior information, then we can also get the estimates for these 2 missing categories. And like we have the result estimates for the 2 missing categories, which is not the case with the classical approach. And then I did some testing with the different prior. Obviously, I traced the one that's a little looser, and I see then that the bias for the standard deviation started to increase by quite a lot. And then if we went more strict, then the standard deviation, it started to underestimate standard deviation. Obviously, this is affected that the in the simulation, I use like 0.75 for the standard deviation, so it's obviously then that affects how much it's the bias. Yeah, so maybe future direction for this is to then try to test with real data more, like try to test with like maybe do some kind of out-of-sample testing with maybe drop one of the clusters, see how it predicts for that, and see how it performs, not just with simulated data, and test more extensive different priors. I now have only normal distribution, but testing other priors, see how they perform and what's the differences. And then obviously we could fit a lot more richer hierarchical structures, so varying slopes, and then maybe you can also like have random terms for the, you can have the threshold parameters varying by the clusters instead of maybe having the additional random term. So there's quite a few of quite a different things that you can test. So yeah, that's that. Thank you.
Okay. Thank you, Aleksi, for a great talk. I'd like to open the floor to any questions that people might have. We got one here to start? Appreciate it. Thank you.
So I have one question about the convergence issues that report. So what I have seen is that often these, for example, the optimizers we use in LM4, I know you didn't use LM4, they tend to be a bit skittish in terms of reporting non-convergence, even though everything is fine. So did you check if the cases where we had like warnings in convergence were actually like problematic estimates, or whether the sampler, the optimizer was just like, you know, overly worried?
Can you repeat that?
So is the non-convergence that you see, the high non-convergence in the optimizers, does it were they really associated with bad estimates, or were the sampler, was the optimizer just like a bit overly sensitive to minor non-convergence?
You are talking this one? Yes. Then you are talking about the Bayesian model? Like
no, the optimizer, the what you call classical.
Well, yeah. Well, the thing is that when I don't remember what function it was, but it like does give the error if it's like not able to properly estimate the standard deviation term. So I'm sorry, I'm not exactly sure that I understood the question, but
we can also discuss.
Yeah, maybe that's better because I can't really think of answers off the top of my head, so we can discuss this more maybe later.
And a minor comment, I would not call it classical. We are like 2026, so I think by now Bayesian should be the classical.
Yeah, that maybe depends. Yeah, I could use frequencies too, but.
Do you have any other questions? Oh, yeah.
So I was curious about the priors that you're using on the locations of the cut points in this model. So what we recommend in our like prior selection overview is, instead of putting a prior on the locations of the cut point, to put priors on the gaps between them. Right, so you look at the difference between the cut points and put a prior on that, rather than putting a prior on the cut points themselves.
I haven't looked into that too much, but
you might want to try that, because it's going to it prevents the mode collapse. So a lot of when the sampling is going to fail is when two of the cut points wind up collapsing into each other, which is going to be the maximum likelihood estimate when you don't have any data. And if you want the prior to stop that from happening, you put a zero avoiding prior, like a log normal, on the distance between two cluster centers.
Yeah, that sounds that it would be better than this, but I haven't run into that problem myself, but yeah, that sounds like it would be better, yeah.
Okay. Are there any other questions? No? Well, let's thank our speaker once again. We'll move on to the next.